я оказался в списке тех, кто попросили сделать это на английском, поэтому будет на английском. Okay, my talk is about the algebra of polynomial vector fields on the affine space and about how it's related to automorphisms of the affine space and in particular to the famous Jacobian conjecture. And the main result which I'm going to prove is to show how this Jacobian conjecture, which is about automorphisms of the n, can be reduced to another conjecture which is formulated only in terms of this algebra. I want to make this talk elementary, so I'll start with defining this object in the title and with learning some basic facts about this. So the first part is the Lie algebra. This algebra which is denoted by vec n. Okay, let us assume that we have the ground field, which is, as usual, algebraically closed and of characteristic 0. And the second assumption is really important. We cannot just omit it. And as for the first assumption about the condition of being algebraically closed, this is probably not so important, but for simplicity we assume it. And to define this algebra, we need the following well-known notion of derivation. And let me briefly recall it. So if we have a K algebra, then first definition, a derivation of this algebra is a linear map from A to A, which satisfies the product rule. So, saying that delta applied to the product A1, A2 is the same as delta of A1, A2 plus A1 delta A2. And the set of all derivations is denoted like this. So it's called K derivation. And the set of all K derivations is denoted like this. Set of all K derivations. And it's known that this set is a Lie algebra. It's easy to show that it's vector space, and also we have just the usual commutator defined by delta 1, delta 2 minus delta 2, delta 1. And it's a direct check to show that this commutator is also a derivation. So this is a Lie algebra. And now I can give the definition of this object, of this algebra. Definition. The Lie algebra of polynomial vector fields on AN is just the Lie algebra of derivations of the polynomial ring, of the polynomial algebra. Okay, x1, x2, etc., etc. And this is the algebra with respect to this operation. Well, it might be not clear why this is called vector fields, because we usually assume that vector fields are something geometric, but we have the following explicit description of this algebra, which is probably well known, but still I state and prove it. Can be described explicitly just like this. All derivations of vector fields of AN are these sums, f1 partial x1, etc., plus fn partial xn, where f1, etc., fn are just some functions, some polynomials. The proposition, so I will give it briefly. First, it's clear that any such sum is a derivation, so this inclusion is clear. And as for the second inclusion, if we have any derivation, then we can just compute it on x1, x2, etc. xn. Delta applied to xi is some function in some polynomial, is some function in this algebra, so sum of I. And we can just define delta tilde just like this. And it's easy to see that, in fact, delta tilde is equal to delta. Why is it so? Just because, by definition, you have this. So they coincide on on the variables. And it follows from here that they coincide on any such monomial. Because we have the product group, if we know how derivation acts on x1, etc., xn, then we know how it acts on their product. And so they coincide on each monomial, and it only remains to say that on constants they also coincide, just because we can write like this. Not delta tilde, but delta. It's by the product rule, it's equal to this sum. So comparing this and this, we see that delta of 1 is 0, the same as delta tilde. So these two derivations coincide on each monomial, so they coincide. And this is the end of this example. And let me write how the commutator looks like. The commutator looks like this. We have I partial xy, and we want to commute it with fj partial xj. Then the formula is simple. It's y partial fj partial xy partial xj minus fj partial fi partial xj partial xj. So it's easily follows from the definition of the commutator. There are some effects which are known for this algebra, and I'm going to mention just one of them. Mention and prove it because it's also easy. So proposition 2 is that this algebra is simple. And returning to this, it is probably it's now probably more clear why these are called vector fields, because in calculus on manifolds these are precisely the objects which are called vector fields. In calculus on manifolds these functions f1 etc. f1 are assumed smooth, and here we talk about algebraic vector fields or polynomial vector fields, which is the same. So it's natural that these coefficients are assumed to be polynomial. And returning to this, I said that this algebra is simple, and the proof is also quite short, so let me give it. So this means that this algebra contains no non-trivial ideals. So suppose it contains an ideal which is non-zero. Then we can take any delta line in this ideal, which is also non-zero. And this delta is this sum. 1 partial x1 plus x2 plus f1 partial x2. And what can we do with this delta? We can, for example, compute it with some partial derivative. We can write partial xy delta. And it's easy to see from this formula that commuting delta with this partial derivative is just taking partial derivatives of f1, f2, etc. So just the sum dfj partial xy partial j for j from 1 to 1. And since this is in I, this commutator is also in I. So we can continue like this. We can take another partial derivative, and then another partial derivative, etc., until all these coefficients fy, etc., fm become constant. Because if at least one of these coefficients is not constant, then it depends non-trivially on some xi, and we can take this partial derivative and get an iteration which is not zero. This ai, a1, etc., an are constant, and we can assume without loss of generality that a1 is not zero. So now we can take the following commutator. We can take this derivation, which lies in A, and commute it with, for example, x1 partial x1. And it's also easy to see that this is just a1 partial x1. And since a1 is non-zero, we have partial x1 lies in it. And then final step, if we can just write like this, if we have any polynomial, xi to the power i1, etc., extended to the power n, partial xj, then it can be written like this. Can be written as a commutator of partial x1, which is in I with x1 to the power i1 plus 1. So this partial derivative lies in I, as we already proved, so this commutator also lies in I. So any such polynomial lies in I. So I is the whole algebra. So it's quite an easy and direct proof. I'd like to mention here that in fact it's a particular case of a more general statement. Give a remark. We can define such algebra of derivations of polynomial vector fields not only for the affine space, but for any affine variety. So if X is any affine variety, then the vector fields, the algebra of vector fields on X is defined just like in this case. So it's just defined as derivations, derivations of the algebra of regular functions on X. It does not look so simply as in this case, as in the case of the affine space. But still we have the following theorem, which was proved by Siebert in 1992, that this algebra is simple if and only if X is smooth. In particular, if we have X mathematical to an, then of course an is smooth, and we see that this algebra is simple. But in general, this is a much more non-trivial statement, about which I gave a talk about 2 years ago on the summit of the laboratory. Well, that's probably everything I wanted to say about the algebra itself. And now I want to pass to the second part of the talk. Which is about automorphisms of AN and how they are related to this algebra. So I can for a title. So it's this the algebra and the automorphism of AN of the affine space. Well, we have the following group of automorphisms of AN, which is denoted like this. By automorphism, I mean a regular automorphism given by polynomials. Group automorphisms of AN. And let me fix the following componentation. An automorphism phi of AN can be written in coordinates like this. Phi of x is phi 1 of x, phi 2 of x, etc. Phi n of x, where x is x1, etc. And phi 1, phi 2, etc., phi n are just polynomials. And the fact that this is an automorphism means that it has an inverse which is also of this form. It's also given by polynomials. Let me just give a couple of examples, just to show which automorphisms there are in this group. First, there are affine automorphisms, which form a subgroup of the group of all automorphisms we have. These are automorphisms which are given by linear polynomials, so they can be written like this. Small maps of this form. X goes to ax plus b1, etc. bn, where A is a non-degenerate n by n matrix. And if n is equal to 1, then it's easy to see that, it's easy to check that these automorphisms are in fact all automorphisms. So affine automorphisms of A1 are the same as all automorphisms of A1. And the second example showing that this group is big in general, that there are so-called triangle automorphisms. Which have the following form. They send x1, x2, etc. xn to these kind of coordinates. X1 is multiplied just by some non-zero number. X2 is sent to a2 x2 plus some polynomial depending on x1. X3 is, on the third coordinate we have a3 x3 plus some polynomial depending on x1, x2, etc. So at the last step we have an xn plus fn minus 1 of x1, etc. x n minus 1. And this example shows that if n is greater or equal than 2, so of course this makes sense not for n equal to 1, but for n greater or equal than 2. We see that this group of automorphisms is infinite dimensional, because these polynomials can be arbitrary. They can have arbitrarily high degree. So these are examples just to show that this group is quite big and difficult to study. study. There are some more specific results. For example, for n equal to 2, it is proved that the whole group is generated by affine automorphisms and triangular automorphisms, but I'm not going to stop on this. Because now I want to show how these automorphisms are related to this delta. Well, suppose you have an automorphism of an. So it's a map from an to an. So it defines the corresponding map phi star on the ring of regular functions from the polynomials to the polynomials, which is given just by the composition. So phi star of f is the composition of f and phi. And suppose we have a vector field delta lying in vector by n. Recall that it's derivational over n, so it's a map from x1 xn to k of x1, etc. xn. And now we can act by this phi star on delta just by conjugation. So we can take this delta and send it to the following expression: phi star inverse delta phi star. In this order, so inverse is here. So this is just a composition of three maps from the ring of polynomials to the ring of polynomials. So it's also a map from the ring of polynomials to the ring of polynomials. And it's easy to check that it's also a derivation. It's also a vector field. This is commonly denoted by a joint at of delta acting on phi. And
Either phi x or delta.
yes, of course, thank you. Let me state this as a proposition whose proof is internet check, but still it's better to give it as a proposition that this ad defines homomorphism. From the group of automorphisms over n to the group of automorphisms of the K algebra. The proof is direct check. In fact, there is almost nothing to prove here. We just need to check that this is a derivation, so it's also a vector field, and we need to check that if we have phi 1, phi 2, then add of phi 1, phi 2 is the same as add of phi 1, add of phi 2. It also follows directly from this formula. Now I'm going to give first non-trivial statement here, which I'm not going to prove, but I'll use it of another statement. Theorem. We have this map from the automorphisms of an to the group of automorphisms of an as of Liège. Rewrite it. I already said that it's a homomorphism, And the theorem says that it's in fact an isomorphism. The theorem was proved by Barola in 2013. And also there is another proof by Kraft again. In 2017. Well, it's quite easy to check that this map is injective, so it will be clear after we rewrite this map more explicitly just in a few minutes. And the non-trivial part is to show that it is surjective, so that each automorphism of this algebra is induced by some automorphism of A. And if I have time at the end of the talk, I'll probably give a sketch, a very short sketch of this proof. Not the original proof, but the proof from this paper. Well, before passing to the Jacobian conjecture, I want to make just a few computations. Well, the question is how to write this map add explicitly. So suppose we have a vector field delta. And we have some phi an automorphism. Then I want to compute this thing. So I applied this map to delta, it's some other vector field. And I want to compute this G1, etc., Gn explicitly. What can we do to do that? We can say that Gi is just the result of the action of this vector field on xi. So we can just write a few lines. It's quite a short computation. I want to do it. So we can write explicitly this star index delta phi star box I, and I need to act on xi successfully by phi star delta and phi star index. Okay, phi star of xi I erased it, but I recall that if phi is an automorphism, then it's given like this: phi 1 of x, phi 2 of x, etc., phi n of x. So phi star of xi is just phi I. No, not xi, but phi I. Then to act by delta on phi I, we just need to look at this explicit formula, and the action of delta on phi I is like this. It's the sum of fi and partial derivative of phi I by all variables. It's the sum from G from y to n, from 1 to n. Fg, Fj, partial phi I, partial Sj. Well, and action by phi star inverse is just the composition of this sum with phi inverse. So now it's almost the end of this computation. If we have a point P in AN, then what can we do? We can try to compute this gi at the point 5p. 5p is also a point in AI. And to compute it, we need to substitute 5p here, and applying phi inverse to 5p, we get just p. So comparing this part with this part, we see that the value of gi at the point 5p is just the following sum. Fj of p and partial phi I partial xj at p. And this computation shows, in fact, the following. Again, let me state this as a proposition, that explicitly this at of phi acts on delta just by the Jacobian matrix of phi. So let me write this proposition. If I want to compute the result of the action of phi on delta at a point 5p, it's the same as taking, I'll first write and then I'll explain what this means. Same as taking delta at the point p and applying the Jacobian matrix of phi at the point p, where by delta p I mean the following comma. Delta p is 1 of p, 2 of p, etc. And the Jacobian matrix is just the usual Jacobian matrix, just the matrix whose entries are partial derivatives of phi 1, phi 2, etc. phi. Yes. Well, this proposition is actually already proved. It just follows from this formula. This multiplication is just like multiplication of this matrix by this formula. Well, it's probably the only computation I want to show this here. And now, if it's all clear here, I want to pass to the third part of the talk. It's about the Jacobian conjecture and its relation to this Lie algebra. The third part is the Jacobian conjecture. Let me recall what this conjecture is about. First, if phi is an automorphism over an, then it has the Jacobian matrix. And if phi is an automorphism, then this matrix is non-degenerate at any point over n. Just because we know that if we compare the Jacobian matrices of phi and phi inverse, this at the point p and this at the point p, then they're inverse to each other. So in particular, they're not degenerate, so it has non-zero determinant. It is a non-zero. It's non-zero at any point, so it's an invertible function. It's an invertible polynomial which vanishes. So since it's a polynomial, it must be just a non-zero constant. It's non-zero for any p in an. So it can happen only if it's a non-zero constant. And the famous Jacobian conjecture is about the converse statement. Conjecture. Suppose you have a map from an to an, just a morphism, from an to an, which we do not know to be an automorphism, but suppose that this condition about the Jacobian holds. So the Jacobian of this phi is non-zero constant. And the conjecture asks whether it's true if phi is not an office. This conjecture is easy to check for n equal to 1, and it's true. And for n equal to 2 or greater than 2, it is open. There are some partial results on this conjecture, but in general it's open. And now I'm ready to state the main result, which I'm going to prove. And this is a result about how to reduce this conjecture to another conjecture about automorphism of this algebra. And this result I'm going to prove. Theorem, which was originally proved by, I guess, Kulikov in 1992, and then by Kraft and Data in the same work as he Kraft. Data in 2017. And the theorem is the following. If any injective phi, which is an endomorphism of this algebra, is in fact an automorphism, then the Jacobian conjecture holds for A. I will write it shortly. The Jacobian GCN is the Jacobian conjecture for the n-dimensional fine space holds. Short remark. When I write here injective, it's the same as just non-equal, non-trivial. Because I proved at the beginning of the talk that this algebra is simple, so any endomorphism of this algebra is either zero or injective. And the theorem which I'm going to prove is the following. If every such endomorphism is not only injective but also surjective, then the Jacobian conjecture follows from this. And the proof is quite nice, and I'm going to give this
You
proof.
consider endomorphisms, not automorphisms?
Of course, yes. Sorry. I guess I said correctly, but I thought it's endomorphism. So just any homomorphism from this algebra to itself. So it's almost automatically injective, but it's not clear whether it is surjective or not. Well, now the proof. Well, before giving the proof of this theorem, let me recall from the beginning of the talk that, not from the beginning, but from some point of the talk, that if you have phi an automorphism of a kind, at this point just an automorphism, then it defines the joint action on the Lie algebra of polynomial vector fields. And we even have this explicit formula, which is not yet erased. So let me rewrite it here. So if we want to compute 5 delta at a point 5p, then is the same as taking delta at the point p and applying the Jacobian matrix of phi at the point, also at the point p. Well, now let me make some changes in this formula. First, let me replace phi by phi inverse. Phi is an homomorphism, so phi inverse is also an homomorphism, so I can write it the same for phi inverse. And let us see what happens. Well, right now I just rewrite this. I just replace phi with phi inverse here, here, and here. And also, let me denote phi inverse of phi of p by q. So after that, this formula is written like this. And here we have the Jacobian matrix. Here I want to replace p with 5q. 5q, phi inverse, delta, 5q. Yes, it's like this. And after that, the final step of this part. I do not change the left-hand side. And in the right-hand side, I just use the fact that the Jacobian matrix of phi inverse at the point 5q is the same as the inverse of the Jacobian matrix of 5 at the point q. And this is applied to the same 5q. Well, I hope everything is correct here. And now the main and the crucial observation is the following. Observation is that the right-hand side is defined not only for an automorphism phi, but for any morphism phi such that its determinant is Jacobian is a non-zero constant. It's not just defined, but it's regular. It's given by regular functions. The right-hand side is defined. When I say defined, I mean regular and regular. For any phi. Phi, which is a morphism over n, such that its Jacobian is a non-zero constant. Well, why it's so? It's quite easy to see why it is so, because here we have the inverse of the Jacobian matrix, and in general, the inverse, the entries of this inverse are rational functions, and the denominators of these entries are just this Jacobian, this determinant. But in our case, this determinant is just constant, so in fact, all functions here are regular. So the right-hand side is defined just assuming that the Jacobian is non-zero constant. Well, and that's actually the crucial observation here. Now let me state a little bit for you what I said here. Well, I think I can say proposition. Well, not proposition, let me say that we have the following notation. If phi is a morphism of an n such that its Jacobian is a non-zero constant, then we can define what I denote by phi tilde. It's a morphism from polynomial vector fields on AN to itself. And this phi tilde is given just by this formula. So phi tilde delta computed at Q is the same as taking the Jacobian matrix of phi at the point Q, taking its inverse, which is also a matrix with regular values, and apply it to delta at the point 5Q. And I just list a couple of properties of this idea, of this correspondium. We can say here more formally that the map sending phi to phi tilde defines in this case it's not a homomorphism but an anti-homomorphism. From morphisms of AN with whose Jacobian is non-zero constant. To endomorphisms of the algebra of polynomial vector fields on the affine space. And I can even specify that I obtain here non-zero endomorphisms. When I say that it's an anti-homomorphism, I mean that we have the following. And also, let me add that if phi is in fact automorphism over here, then this phi tilde is just the same that as at of phi inverse, which was defined at the beginning of the talk. Well, this claim is easily follows from this definition of this phi tilde. Well, and now I'm going to give you the proof of this theorem, which is now going to be quite short. This theorem. We have a morphism from AN to AN such that its Jacobian is non-zero constant. And I want to prove that this morphism is an automorphism, assuming that every injective endomorphism of the algebra vector fields, of polynomial vector fields on AN is an automorphism. Well, we can using what's written here, we can we have eta tilde, which is an endomorphism from this algebra to itself. It's easy to see that it's non-injective, it's non-zero. Well, because we can see it, for example, just from this formula. Here we have a non-degenerate matrix. So if we apply non-degenerate matrix to a non-zero vector field, we also obtain a non-zero vector field. So it's non-trivial. So, assuming that this conjecture holds, it's in fact an automorphism. And now, using another theorem which I stated some time ago. We know that any automorphism of this algebra is induced by some automorphism of an. So there exists by theorem of Paulin, which was stated some time ago. There exists phi, which is an automorphism of an, such that each tilde is just induced by this phi. Well, and also we know, it's even written here, that if we compute phi tilde defined like this, then is the same as head of phi inverse. Well, so now if we take the composition, phi and eta, then it's also written here. We have eta tilde composed with phi tilde, which is the same as head of phi composed with head of phi inverse. So it's just identity. It's identity on the Lie algebra. Identical. Well, and let me also denote this composition of phi and psi. So here we have psi, that psi tilde is identity, and the final claim is the following: if psi tilde is identity on the Lie algebra of polynomial vector fields, then in fact psi is identity, with the identity on AN. And if we prove this claim, then everything follows, because we have this is identity, this is an automorphism, so eta is also an automorphism. And this is exactly what we want to prove here. Well, let us just prove this claim. It's very short. So let us look here. We have this formula. And let us replace phi with psi here. And let us rewrite this expression using the fact that here we have that this eta tilde is identical. So we will just have the following. I have delta computed at q is the same as taking delta computed at psi of q and applying the Jacobian matrix of q of psi at point q inverse. And this formula holds for any delta, for any polynomial vector field. Since it holds for any polynomial vector field, we can take, for example, some simple vector field. For example, we can take delta equal just to partial derivative, partial xi. In this case, its value at q and at psi of q are the same. So we have delta q the same as the Jacobian matrix computed at q. I just use the fact that delta computed at psi of q is the same as computed at q. And since it holds for any x1, etc., xn, it follows from here that the Jacobian matrix of psi at the point q is identity. And actually, that's enough for us, because now we know that psi is an isomorphism over n, such that its Jacobian matrix is identity. identity at any point, so it follows that psi is a translation. We did not prove yet that it's identity, but at least it's a translation. And actually, it's sufficient for us, because the translation is an automorphism. And also, you have psi composed with beta is equal to psi. This is automorphism, this is an automorphism, so psi equal to phi inverse psi, eta equal to phi inverse psi is also an automorphism. And just let me say that actually we can show that this psi is not a translation, but is not just a translation, but an identity, just because after we proved that this matrix is equal to I, we know that delta Q is the same as delta psi Q for any point Q and for any delta. And of course, this can hold only if psi of Q is equal to Q. If these are different points, then there is a vector field which has different vectors at these points. So psi is actually an identity. The identity. Well, and that's the end of the proof.
So there are some specific algebras, say, valid, how to pronounce correctly, maybe valid algebras,
yes,
which are non-commutative but associative, and which are generated by polynomials and partial derivatives.
Yes.
And Bixby conjecture claims the same, that any non-zero endomorphism is an algebra.
yes.
And this is also related to Jacobian conjecture. This was proved recently by Alexander Zhiglov, but in a particular case of one variable which is not connected with this conjecture, this Jacobian conjecture. And here's the same type of result. Also infinite dimensional, simple, but not associative, but Lie algebra. And the same property. Any endomorphism is automorphic. So this is somehow important property which is very difficult to do.
More questions and comments? I have small questions. And is the second line on the yes, it is phi or
It is